Hello, Tyler. Hello, Camille. Hello, Crystal.
Morning.
Morning. Oh, it's quite a sound. Yeah.
Hi, morning.
Hello. Hello. I hope your vacation break went well, and I hope you were happy with your exam in the last part. I was thinking back about our little discussion, which I didn't publish on YouTube because I was not confident in myself. But you were asking about like if one particle can occupy one state or many particles can occupy states. I think this verbal was formula was relating to Fermi-Dirac and Bose-Einstein distributions. Click something. Thermal distributions for electrons and for phonons or bosons. Okay. No? Yes? Okay. Kind of yes. Okay. So let me also share the plans. If I was promising to send you some emails during the break, but I was taking break myself. I didn't send anything. So let's maybe make a little straw vote or just a little not final, but are you more leaning towards doing projects or you are leaning more towards exams and so I see Crystal, but what about the rest? Chamely?
Yeah.
Do you like exams or project reports better?
Projects.
Projects, okay. Tyler?
I believe projects too.
Okay. John?
Project.
Okay, by majority. So thank you. It makes me happy because it is easier for me. Projects are easier than mumble something here. So I also have a wild idea that can be, if administration will hear, I could be punished. my idea was to accompany lectures with some informal labs, but I think you are busy, and maybe if instead we just do one lecture in class and one in the computer lab, what project you'll spend as you were planning to spend your time, and we will have even less class material, but during the lab you will do projects. So I'm not sure about this Wednesday, but starting from next week on Wednesdays we will walk to the computer class in the barbecue 132, and the project first time we'll just learn about MATLAB software which is installed there, and you all are welcome to and encouraged to install it on your personal laptops, but it is not needed. It is available there. And then I will share some codes that you will launch and just analyze data, and then it will our mutual life easier. And so, okay. And I'll talk more about projects, but I'll provide some minimum about thermodynamics so that I can report to my superiors that I did my job, and you got your course. So when we were meeting here 2 times, and once I was drawing stoves and pots, right, with pistons, and another time we were deriving the adiabatic dependence, so that pressure times volume to some power equals constant, and we needed this idea, this process, to complete the cycle for the heat machine to make closed loop. And so we were voting for exams versus projects. What is your projects? Okay, then we have not vast majority. We have just all as one. Okay, good. No contradictions. I'm also for the project. So heat machines can be the dumbest closed loop cycle with Carnot with isotherms and adiabatic. And isotherm is more shallow, adiabatic is more steep. But if we have two of each, we make a closed loop, and as the heat machine cycles over, it can convert heat into the work, right? So the tentative plan, and again, I'm doing it for the first time, but tentative plan is that we get, we already got this heat machine motivation. We will get these two processes, isotherm adiabat, and then we will go over cycles and introduce efficiency of heat machine. And then next step will be to like laws of thermodynamics first, second. And to my understanding, there is a concept of internal energy that sometimes is very comfortable to upgrade to some chemically relevant potentials like enthalpy. Probably the course will last longer, but I cannot look so far too far forward. So it's like a couple of weeks when. So last time we got PV to the power gamma equals constant, and today we need to do PV equals constant as a term, right? So ideal gas law, right? And I have no doubts that you're well aware of this dependence, and if you will be under stress, you would derive this equation if needed, or you can reproduce this equation yourself, right? So I have like a sketch of logical steps how to get it, but maybe you can share your vision where ideal gas law comes and how we should derive it. Let me quickly write just one thing: motivation. Convert heat to work, right? So it is in the middle of Carnot cycle. But any word about ideal gas law and isothermic process? So where it comes from? How, if, for example, suppose I am not prepared for 3 days, where I should start thinking about it? Some of the another version is like PV.
Are you asking where the ideal gas law comes from, or how it relates to the isotherm?
Where it comes from?
From the different gas laws, Boyle's, Charles, and Gay-Lussac's.
Okay.
It's a combination of all of them, because if you put them all together, you'll get the PV equals nRT if you like set each one of them equal to each other and merge them all.
Wow, interesting. It's correct, and it is a phenomenological approach. It's good. What other any alternative ways where it may come from? Just share any of the memories, because I will go slightly different path, but maybe you are aware of it. And do not hesitate, bring in some wild ideas. Like the container with gas, it acts like a spring. We try to compress it and it resists. Like the door, there are machines that prevent doors from slamming, and some of them are pneumatic, so it acts to some sort of like a spring. So what is the reason for pressure, and why?
Collisions of the gas particles hitting the container.
Exactly. I do not need any ideas, even if you have something better. Yes. So let's chat about gas particles hitting the container. And I apologize for repeating some basic things. I have no doubt that it is something that you did in the high school. So the so here is my how to say flow chart of steps. So I plan to draw a particle. Well, yes, I will draw a particle in a container, assign velocity, draw a piston, and then we'll go over momentum of particle, pressure acting on the piston, connection between pressure force. Consider instant of collision as Crystal suggested. Then we will need to take into account that there are multiple particles to count for amount of particles that hit the piston, and then look for overall amount of momentum that each particle communicates to the piston. So we basically need to multiply momentum from one particle times total number. And then we will bring in a concept of kinetic energy and from translational motion, and there will be, well, thermodynamics is not a new breakthrough science, but we will pretend that we have, oh, what a surprise. These two things are really similar to each other. We should derive an equation. And then we'll roll over this stuff backwards. Like we start momentum, pressure, force, and then we go backward, force, pressure, internal energy, and then we'll connect them and arrive to isotherm. So first thing is to draw yeah, let's do it the same way as we were doing it before. So we have this cylinder, we have a piston with a mass, we have a stove, and here we do have one gas particle. So this gas particle, if temperature is above zero, it typically moves, right? And it moves randomly in some direction with velocity v, which means it has component in each of three Cartesian directions. You can call this one Vx or Vz, whatever you like. X, V, Y, V, Z, right? And we are considering, well, let me draw it a little. Now it looks like it should collide with the wall. Let me draw it in a little simpler way. So that it will go towards the piston. So if you move, then hit the piston and then reflect, right? And what happens? I was thinking about a car driving against a lot of flies, but it is not right way, not gentle to collisions are in everyday life is not a good instance to give an example, but maybe if a sportsman is getting a ball from a partner, but the partner is so strong that the ball goes with the high speed and it kicks, right? I can feel if especially if it is not baseball but something bigger for basketball, it can push me a little bit, right? And if the whole team will start throwing basketballs into me, it can smash me into the ball eventually. So same stuff here. So when a particle hits the piston, it collides and passes part of its momentum to it, and then report back. So we need to discuss it. So what is momentum?
Mass times velocity.
Good. So lowercase p, mass times velocity. Good. And we can tell it that it is 3 components: mvx, mvy, mvz. Good. So we intuitively know that this big mass, heavy weight on a piston doesn't come instantly down. It experiences pressure from this gas, right? So we need to define what is pressure. And we can say that area of piston is capital uppercase letter A. So any ideas what is, what are the units for pressure when you pump the tires?
It's force over area.
Yes, force over area. And yes, and if you take imperial units, which are used here for gas stations, pounds per square inch, right?
Yeah.
So pressure, and here I know it is a little confusion, but momentum is lowercase, pressure, let's use uppercase. So force per area. And if we would be very meticulous, we would take care of force and area and angles. Like we do not need to dry our brains right now, but there are possibilities that force is tangential to the piston, and then it will not move it anywhere. So the pressure needs to be. So typically, people define a vector which is perpendicular to the surface area and call it like A as a vector. Then the force is also a vector, and then one makes a vector product to define the direction. But we'll live simple life here. Okay, now what is force? And it's not a trap question, nothing sophisticated. Just tell anything you like. Huh? MA. And what is A? Yeah, okay. And what is acceleration? It's a change of velocity. So time derivative of velocity, right? And no one will punish me if I move this derivative in front of mass. So if I'm not designing a rocket engine, it is possible to do. If we do rocket engine, it is not possible because rocket loses weight, right? So we put dt mv, and we already defined that mv is a momentum, right? So derivative of momentum over time is force. So and it goes to common sense, right? If something changes my momentum, it means someone applies to me a force. Like if I'm running and policeman holds me by shoulder, I change my momentum. He applies force to me. Right?
Could we zoom in on the board a little bit by chance, please?
What?
Please zoom in on the board a little bit.
Larger font?
Yeah, like does the camera let you zoom in on the board at all? So you can see it. It's really hard to see them.
This camera is not zoomable.
Gotcha. Okay.
And
Never mind.
I can write out a bigger symbol. right? I'll try. Maybe if I'm writing here, I will quickly move the image, like copy, paste, and shift here, and then right here, and we will use one board per meeting here. Okay, and then I'll write this bigger font here. Yeah,
Thank you.
Thank you. I was thinking about it myself as well. Okay. So we can tell it like change of momentum in finite difference over certain time, right? And if a particle hits into the piston, since the particle is infinite times lighter than the piston will not move with noticeable velocity. So by conservation of momentum, the particle will start moving in the opposite direction. And the total amount of the change of momentum, so I need this delta p. Delta p from one particle will be so before momentum, before collision, the momentum in the x direction, mvx. After, it will be minus mvx, right? Because it will move in the opposite direction. So total will be 2 mvx. So by collision of each particle, and we do not tell that all particles cooperatively move up. They may move left, right, up, down. We just take projection on the direction towards the piston, and each of them will communicate the same amount of, well, this much of momentum. They will contribute to, through momentum, they will contribute to the force and to the pressure. And our goal is to relate pressure and internal energy, or pressure and volume, and get the ideal gas law. Okay, so we know the amount of change in momentum or contribution to the force from individual particle. Now we need to count the number of particles that hit the piston. And we need to count amount of particles hitting per unit of time. So I don't know how many particles are there. And when someone is running wet chemistry experiment, it's possible to introduce a variable, but typically one operates with concentration, right? So we can introduce concentration as number of total number of particles per overall volume. Concentration. Of uppercase V. Now, here is the only non-trivial part in today's discussion. Which fraction of the overall number of particles will hit the piston? So maybe what is delta n? And if we assume that all particles or gas molecules are equally distributed along the volume, right? We can tell that the amount of particles that hit the piston can be symbolically placed here's the piston, can be symbolically placed in a fraction of volume, delta V. Fraction of volume of all particles that will arrive to hit the piston in the given time. So all particles which will arrive in time. So now we work as a train scheduler. So how do I know if the particle will arrive? I can play with distance that the particle will travel. So if our designated time is delta t and the velocity of given particle is vx, then it will travel for vx times delta t, right? Now, I don't know how, it's quite a simple idea, and probably you already know where the train of thought will go. But I have difficulties even to explain it for myself in normal language. Maybe let's invert time and assume that at the initial moment of time, all particles are stick to the inner surface of piston. Then we go backwards in time, and they all start departing in different directions, right? And then after delta t is passed, we measure how much volume they will take, right? And now we can again invert the time and look all particles that and invert velocities that take this volume originated from hitting the surface. So basically, we need to compute the delta v is vx delta t times a. So compute the volume that is taken by this travel distance times the area. Please let me know if more comments are needed, because I feel like I did scramble the explanation. Does it make sense, or you need more comments? Make sense? Okay. So if the volume fraction of volume is this velocity, time period, and area, then we can use Archimedes law, right? So we can multiply concentration times volume of these particles that are about to hit the surface, right? So total number of particles divided by volume, multiply, and then I'm going to plug in this stuff here. So Vx delta t times area. So no objection. Was there some?
Yeah, so the last one, if we substitute in that last bit for delta v, where does the solid v come from? So it's n over v times what we just looked at.
So uppercase n, total number of particles. Uppercase v is total volume before we start doing anything with it. And lowercase v with subscript x is projection of velocity. So there is a little confused because letters V are used in dual fashion. Uppercase for volume, lowercase for velocity.
Okay.
And because in English they both start with letter V. Okay. So now we're almost done. Well, I will spend about the same time as we did spend, but there will be nothing new. We do have the change of momentum through heat of one particle, and we have total number of particles that will hit the piston per unit area. We basically need to merge these two boxes together. So overall momentum per time will be summation of little contributions from each particle hitting the surface. Okay? Or I can just put this number of particles that hit the piston times delta P. Okay? And now is nothing but blindly plug in this, these two boxes. So total number of particles, volume, projection of velocity, time increment, area, factor 2, mass, projection over x. There is a little trick which is easy to forget. One needs to put factor 1/2 into here because if you take absolute value of velocity, half of particles move upwards, half of particles moves backwards. So 1/2. And we plug 1/2 here, and then we cancel this factor 2. So now there is a little surprise that will drive us to the next step. So here we have x component of velocity, and here we have x component of velocity. And we also have mass. So what is mass times velocity squared?
Your momentum? No, that's not.
mv squared divided by 2. Yes, kinetic energy.
Oh, yeah.
So we already feel that this stuff will be related to kinetic energy. So we are on the right way. And kinetic energy is temperature. So momentum, whatever we find, change of momentum, force, and pressure will be soon related to kinetic energy of gas and to temperature, right? And it is just by consolidation number of particles and transferred momentum, we just got this product. So it is from technical point of view, it is a main discovery. Okay. This is change of momentum, total change of momentum. But we do need momentum per time. So we need force, which is change of momentum over delta t, right? It means I'm going to rewrite the same stuff, but I will remove delta t, which means the force and pressure will be irrelevant how long we set the schedule for particles to hit. Even if it will be very small time, it's if we are nerds and geeks of calculus, we would put limit delta t equals to 0. So number, volume, velocity squared, mass, area. That's it, right? Okay. And we do need force per area by our definition of P capital, momentum. So we need force divided by area. So we do the same thing, we just remove the letter E. Right? So total number of particles, volume, projection of velocity in x direction, and mass. So we feel with our instinct that something is very close, and there are just couple of technical steps. So I'm going to keep this box and this artistic design of a piston and remove the middle part to get a little bit space for writing. Okay. Do we have power to issue a decree for a molecule in which direction it must move? I don't. So it means that kinetic energy of motion in each of three Cartesian directions should be the same, right? And if I add all of them, no, do not call me at this time. Sorry. And if we, so equals some constant. And if we add all of them together, it will be just this constant times 3. But this constant is equal to kinetic energy of translational motion towards piston. And everything is set up, not in a bad sense. It is not a trap for us as humans. But this derivation, you see here factors 3/2. And you remember it from ideal gas law. So now this 3 translation degrees of freedom and 2 from kinetic energy, they will be, we will inherit them in the subsequent equation. So this stuff together is kinetic energy of one molecule, right? And mvx squared over 2 mvx squared, because we need it later, will be kinetic energy of one molecule to the power 2/3. Multiply left and right by 2, divide left and right by 3. Okay. Now I can plug in this stuff into this stuff. So the pressure plug in. Pressure will be total number of particles, total volume, and then instead of this mass times velocity squared, I will plug in 2/3 kinetic energy of one molecule. So translate if it is translational. The rotations and oscillations do not contribute to this. Now, so we are done with this, and we can introduce internal energy as kinetic energy of all molecules in the container. So if you just multiply kinetic energy of one molecule times total number of molecules in the container, you can call it letter U. And the word internal maybe not the best choice, but it is historically associated. Okay. And now we can plug in this box into this expression for momentum. So we have momentum 2/3 U divided by V. And then we can process this equation in two forms. One form, if we do it as multiply left and right by volume and do PV equals 2/3 of internal energy equals constant. And this is our isotherm, right? If temperature is not changing, internal energy is not changing, and product of pressure times volume is a constant. So basically, it is where we wanted to arrive. And we can also write it in a slightly modified form. We can just flip the factors and tell U equals 3/2 of PE. And if we know nothing about molecules, if you have doubts that matter consists of molecules, we know only real observables like pressure, volume, temperature. We can use this as a definition of internal energy. So something inside the container that is proportional to product of pressure and volume can be defined as internal energy of the gas in the container. What can we do with this stuff? What could be the benefits? So we can plug this dependence of the isotherm and the adiabatic process into the Carnot cycle and use it to compute efficiency of the heat machine. And if we define thermodynamics as part of knowledge, engineering part of knowledge to optimize efficiency of heat machines, it could be most natural next step. Another direction to move forward is to maybe try to summarize humans' observation into empirical laws, like how the heat communicated to this heat machine, the work done by machine, and change in the internal energy connect to each other. So which will be basically laws of thermodynamics. But I don't know about you, but I would feel that it is enough for today. So do you know where is QVB 132? No? Yes, we can. I'll ask if there will be questions and I'll answer quickly. And if no, right after the meeting, I can close this Zoom connection and you can briefly make a quick excursion so that when it will be announced, you know where to go. Okay, so meeting is done. Everyone knows what is isotherm and adiabatic process. Any questions are welcome. Question 1, question 2. questions we solved. No questions. Meeting is done. I'm finishing the Zoom connection and we'll make a slow walk towards the PVV 132 if if anyone has doubts about it.
Did you say QBB?
Yes, QVB.
Okay, not our computer center in lab.
No.
Okay.
Because I checked on Wednesday that they do have MATLAB installed with guarantee.
Okay.
Okay, so is it do you permit me to quit the connection?
Oh, yep. Thank you.
Okay, thank you.
Thank you.
Okay, thank you. Bye bye.
Hey.
Bye.